Welcome to the second session on Boolean algebra. In this session we just have two topics to cover: relations and functions, and we will use the Cartesian product that we defined in the last session to explain these concepts. There are 10 slides in this session. It takes a little bit longer than the last session, at about 18 minutes to complete. In the last session we defined the Cartesian product between sets, and that allows us now to define a relation between two sets. So a relation between sets A and B relates elements of set A to elements of set B. And a relation between sets A and B is simply a subset of the Cartesian product. So it is a set of ordered pairs A, B, where A is an element of A and B is an element of B. And it is simply a subset of the Cartesian product. We can just as easily define a ternary relation on three sets, and it is the subset of the triple product that we discussed. We can also have a binary relation on a single set A, and in that case it will be a subset of the ordered pairs of the Cartesian product of A with itself. With the definition of a relation between two sets A and B, we can also define the inverse relation. So we saw a relation is simply a subset of the Cartesian product A times B, which is a set of tuples A, B. And now we can use that to define the inverse of that relation. So in order for the inverse to exist, the relation has to exist. And the definition is: the inverse relation is the set of ordered pairs B, A that are part of that are a subset of the Cartesian product B times A, given that the pair A, B is an element of the original relation. So again, we have the set of ordered pairs B, A, subset of the product B times A, given that the tuple A, B is an element of the original relation. It sounds a little bit complicated, but all we're really doing is reversing the order of the elements in each of the ordered pairs. And we have a subset now of the set B times A, and before we had a subset of the product A times B. Let's look at an example relation. Let's consider the set X with just three elements, the numbers 1, 2, and 3. Then the Cartesian product of X with itself is the set of 9 tuples, where we combine an element of X with another element of the same set. Remember, the Cartesian product, the cardinality of the Cartesian product, is the same as the product of the cardinalities of each of the sets in the product, which is 3 times 3 here. So we have 9 possible ordered pairs. Now, a relation is any subset of this set of tuples. And let's look at the less than relation. That means that the first element in the tuple must be less than the second element. Not less and equal than, but just less than. That leaves us with 3 ordered pairs: 1, 2, 1, 3, and 2, 3. And let's observe here that the element 1 relates to both 2 and 3. So this is a one-to-many relationship in that sense. But also we see that the element 3 in the y position is related to both 1 and 2 in the x position. So both 1 and 2 relate to 3. So this is an end-to-end relation. And that will become important later. We can define the same less than relation on the Boolean domain with just 2 numbers in it, but there is only one ordered pair in the result, and that's 0, 1 pair. We can also think of a binary relation as a set of 2D positions. Let's first define what a position is, and let's start by thinking about a position in a single dimension. And let's define a position as an element of the set in question, So if we have a position in real space, the real numbers, It's simply a one-dimensional position on the real number line is simply an element of the set of real numbers. For example, the number 0 is a position in one-dimensional real space along the real line. Now we can define properly what a two- or three-dimensional position is. The three-dimensional positions that we have likely seen in textbooks and other places, the tuples x, y, and z, are in fact elements of the Cartesian triple product of the set of real numbers. So R3, as we commonly see it, in fact stands for the triple product of the set of real numbers, and it equals the set of ordered n tuples, three tuples, x, y, z, given that x, y, and z each are elements of the set of real numbers. So function input can also be seen as a set of positions. If we have a binary function, it means it takes two input variables. The set of inputs for that binary function is the set of 2D positions. For example, a two-dimensional or binary function on the Boolean domain, a function with two inputs, takes as input the set of ordered pairs that are elements of the Cartesian product of the Boolean domain. So the set of tuples x, y, where both x and y are members of B. So binary relation can be seen as a subset of 2D positions this way.